As we wrap up our study of the kinematics of particles, we finish up with the topic relative motion. And the concept's pretty easy to understand if we look at a simple example here. Let's say that you're in car A and you're heading east, which we'll define as the positive x direction, at 50 miles per hour. At the same time, a car is going the other direction, it's car B, at 40 miles per hour. Well, if you look out the windshield of car A toward car B, it appears to be heading towards you at 90 miles per hour. We call that apparent velocity, the velocity of B relative to A. We can write that as a vector by saying velocity of B relative to A, we write it there with the subscript B slash A, B relative to A. And so our equation, velocity of B relative to A, is the velocity of B minus the velocity of A. So in this case, since the velocity of B would be minus 40I, and the velocity of A would be positive 50I, then the velocity B minus velocity of A gives me minus 90I. So again, from A, it looks like B is approaching, which means going from right to left at 90 miles per hour. And if we switch those around so that if we're in B looking at A, then the way we write that relative velocity equation is always in that order. A relative to B is equal to A minus B, whereas B relative to A was B minus A. And so in this case, we just switch those numbers around and we end up with a positive 90I. And so what that shows is that the velocity of B relative to A is negative the velocity of A relative to B. And similarly, there's an equation for relative acceleration. We won't use that too much in this section. We will find out that these relatively simple equations are really powerful when we start looking at rigid body motion, rigid body machinery, rotating machinery. Especially we can work from one point to the other within that mechanism. Now, a lot of the problems that we work this time are pretty simple in that we're given the velocity of A and the velocity of B, and we just have to do the vector subtraction. But we'll look at another example problem where the unknowns are a little different. So let's say a plane can fly at 300 miles per hour in still air. So we'll say that's the speed relative to the air. At the same time, we'll say the wind's blowing from west to east at 40 miles per hour. But your flight path, you want to go exactly south to north, even though the wind's blowing you toward the east. So you need to know what direction to point the nose of the plane, and also what the speed is as you travel from south to north, in other words, the ground speed. Now, if we look at those unknown and unknown quantities as vectors, we said the plane's airspeed is 300 miles per hour. But again, for us to go south to north with the wind blowing us, we're not sure exactly what direction we need to fly. The air, of course, 40 miles per hour toward the east, so we know both its magnitude and its direction. And we don't know how fast we're going to be flying from south to north, but we do know the direction, of course, is going to be straight from south to north. So there are two unknowns here, but one of those is the direction and one of them is a magnitude. And now remember that anytime you have a two-dimensional vector, that becomes two scalar equations. So you can work this with components, or we can draw it up on a vector sketch. Now remember, here's our equation. The velocity of the plane relative to the air is the velocity of plane minus the velocity of air. Now if we rearrange that to be an addition, then the velocity of the plane equals the velocity of air plus the velocity of plane relative to air. And so we'll place those vectors tip to tail on a sketch here. Okay, the velocity of air is 40 miles per hour west to east. The velocity of the plane relative to the air, we can fly at 300 miles per hour, but we're not sure exactly what the direction is there. When we add those two together, we get the velocity of the plane from south to north, but we don't know exactly what its magnitude is. So using the law of sines, law of cosines, we can solve for those two unknowns and find out we have to fly at about a 7.7 degrees to the west, again, because the wind is blowing you from west to east. And so the actual speed going from south to north is reduced a little bit from the 300 down to 297 because again part of the speed is just to counteract the 40 mile per hour wind. So next class, after the first test, we're ready to start with the kinetics of particles. So in this case, we'll be using the well-known equation, sum of the forces equals mass times acceleration. So if we know the forces acting on a body, we can calculate the acceleration. But once we do that, of course, the stuff that we've learned so far is still valid. So once we know that acceleration, we can use the things we've learned so far and relate that acceleration to velocity and position.